Hello. Here we will talk about integration by parts, or per partes, if you want some Latin. Now, you can express this rule in several ways, and I'm not just talking about choice of letters. There are actually two distinct versions. One version works with derivative as a tool, and the other one works with total differential. But in fact, this is not really the important part. The important part is the mechanics, the basic idea of integration by parts. So let's have a look at it. We have an integral, and the function is actually written as a product of two parts. Sometimes you get it like that, and sometimes you have to work a little bit on it. Now, what does integration by parts do to this? Well, one part is actually differentiated. So that's something we should think about. And then there's the second part, and to get here, we have to integrate. So that's another aspect. Now, what is our motivation? Our main motivation, the base motivation, is this differentiation. When we do integration by parts, we actually expect that this square, this little part of the product, improves after the differentiation. And if it disappears, that's even better, but let's be modest. So when we are choosing integration by parts and how to set it up, we are thinking, is there something in our integral that can be improved by differentiation? That's a very important question. And then there's the secondary motivation, which is sort of like a limiting motivation, because this other part will be integrated. And we know that integration is not easy. So we are actually restricted to situations when this integration is sort of easy, not too messy. And moreover, it will get copied over here. And then we will integrate again. So what we like to see is that after we integrate and copy it, the resulting expression is not too bad. In particular, it should cooperate with this derivative in some way. So these are restrictions. And they are actually quite good because they are strict. There are just few types of integrals that can actually work like this, which makes it easier for us to recognize them. So the integration by parts method is sort of convenient because you learn something like two basic types, and you have a very high probability that you can judge correctly whether to use it or not. So let's have a closer look. Do I know some function which can be differentiated and it improves markedly? And the answer is yes, polynomials. If I take a polynomial and I differentiate, the degree lowers, and if I repeat doing it, it disappears entirely. That looks good. So a polynomial, that's a good choice. Now, the second component gets integrated. Do I know some functions which, after integration, are still nice? Well, that's actually a fairly short list. Let's say sine of x and cosine of x. Just turn one into another by integration or differentiation. So that's a good candidate. Another nice function is the exponential, and I can put a linear factor here. So it's e to ax plus b. That's a typical case. Anything else? Well, not really. So this is the basic type. When I see an integral, and it's of this form, polynomial multiplied by sine, cosine, exponential, then essentially there is a 99% chance that the best approach is using integration by parts. Okay, is there some other possibility? Well, there are a few more functions which actually change the nature by differentiation, and usually the outcome is slightly more convenient. One particular example is logarithm. Logarithm of x is a nice elementary function, but in integration it actually causes troubles. But if we differentiate it, it changes into 1 over x, which is like a ratio of polynomials. This may be nice. So this is another good candidate for a part which gets improved by differentiation. However, how about the other part? We would like to put something here which does not really get much messy when we integrate it. And moreover, it should collaborate well with 1 over x, which is the derivative of logarithm. And 1 over x multiplied by sine, cosine, or exponential, this is not a very easy integral. This is not a friendly integral, definitely not. On the other hand, if there is a polynomial here, we integrate and the degree goes up, which is usually not so nice. But then it gets divided by x. Well, sounds good. Let's put a polynomial here. So that's the second basic type. A polynomial multiplied by something which changes using a derivative into something which is, let's say, compatible with a polynomial or friendly with a polynomial. There's another function like that. It's arctangent. And also arcsine is sort of a function which works well with polynomials like that. So that's the second basic type, and that's it. There are just two basic types of integrals which can be handled well using integration by parts. And there are some exceptional integrals as well, but I wouldn't call that a method. This is a method. You see this type, you apply integration by parts. And then there are tricks. So sometimes you can apply integration by parts also to other types, but these are tricky things and you cannot somehow show them nicely. Okay. Is it really worth doing an example like that? Probably not, because that's too easy, and I'm sure you did it at school. So once you choose the right integral, applying this mechanism is just a form of work. So let me instead show you one integral which is, let's say, a little bit tricky, just to show you how things can be done. Here we have an integral, and at the first sight it doesn't fall into the two types that we had here before. This is not a polynomial multiplied by exponential sine cosine, and it's not a logarithm multiplied by a polynomial. But at the second sight, it actually is a logarithm of a sort. Perhaps the +1 will not really cause any trouble. Multiplied by a polynomial, and a very nice polynomial. Okay, so that's the second type. And we know that we would want to improve or change the logarithmic part by differentiating. And then we have no choice. We have to take the remaining part, whether we like it or not, and integrate. Actually, I like it. That's the good news. So, how does it work? Well, essentially, you would have to memorize the mechanics or find some way to see it. My way, I sort of feel that by integrating, functions go up, and by differentiating, they go down, because that's what happens with polynomials. And I sort of feel that when I do integration by parts, first I have to go up. So this part is just copied. And this one gets integrated. That's the step up. And now there is minus integral. I'm going to copy the part which went up, which is x. And to balance things out, this one goes down, I differentiate. That's a simple derivative. Okay, let's have a look at it. This is the part which is already done. And this I have to differentiate. And I look at it and I can see that it's actually a ratio of polynomials. So I should apply partial fractions decomposition formally. Let's have a look at it. Okay, I copy the part which is done. And how do I apply partial fractions decomposition? Well, actually, there is the tricky part. I can only apply it if the degree in the numerator is less than the degree in the denominator. And this is not the case. Here, both degrees are 1. So there is a trick for it. We simply divide and use the remainder. Or, if you want, you can look at it this way. X over x plus 1 is just x plus 1 minus 1 over x plus 1. And then we divide. So it becomes integral 1 minus 1 over x plus 1 dx. And this integral is very simple. Let's go. X times logarithm x plus 1 minus. We integrate 1, which is x. Minus minus is plus. Logarithm x plus 1 plus c. And finally, we have to worry about validity. Well, logarithm only accepts positive numbers. So x should be bigger than -1. And that's it. That should be the answer. Okay? So that was a nice integration by parts. Now the question is, can you do it in some different way? There are some formal approaches. Some people use a special notation to use integration by parts. So I will try this again using a slightly different notation. And I will also show an interesting trick, because what I did here, I did everything in a straightforward manner. So when I was differentiating, I just took derivative, and there is not much choice there. And here for the integral, I choose the first thing which came to my mind, which is the traditional way of doing integration by parts. So let me show something slightly less traditional. Let's try it again. There is a certain way of writing integration by parts which is fairly common, and perhaps you learned it as well, and it goes like that. You assign letters to each component in such a way that it facilitates integrating by parts. First of all, this part is supposed to be differentiated, so I will just call it, let's say, f. This part should be integrated. It should go up. So somebody probably already differentiated before it got here. So that would be g prime is 1. Now perhaps you use different letters, u and v, or perhaps you used u here and dv here. Doesn't really make any difference. The mechanics is still the same. Anyway, what we should do, we should sort of pass to the opposite side. So we have f here, we want to know f prime, and we have g prime here, we want to know g. Okay, here we differentiate, very simple. And here we have to take an integral, but here's the trick. I am not taking x, I'm taking x plus 1. A little bit of foresight. Why? Because I know that these two things will be combined in the new integral. Let's have a look at it. Okay, integration by parts. These two are multiplied. Logarithm x plus 1 times x plus 1 minus integral. And here we combine these two. 1 over x plus 1 times x plus 1 dx. Wonderful. Wow, they cancel. Isn't that nice? Logarithm x plus 1 times x plus 1 minus integral of 1 dx. And this is x plus 1 logarithm x plus 1 minus x plus c. And we figured out before that x should be more than -1. Now, when you look at this answer and compare it with the previous one, you will see that they are actually the same. If you multiply out, you will get logarithm multiplied by x and logarithm separately. When we were doing it before, we actually had this individual logarithm with absolute values. But if x is larger than -1, you don't need those absolute values. So really these answers are the same. By the way, if they were not the same, that still shouldn't be a problem, because this is just some antiderivative. And we know that we can have more antiderivatives, and they can differ by a constant. So for instance, this could be larger than the previous answer by 13, and it would still be okay. But it's the same. That's nice. Anyway, this is the example on integration by parts, and there is not really much to it. That's all. You just have to recognize that you are supposed to use it by fitting it into one of those two types, or perhaps there is a little trick involved, and then you just follow the procedure. And if you get lucky, the new integral can be handled. Sometimes you cannot handle it right away, you have to work a little bit more on it. Perhaps sometimes you have to repeat integration by parts. This happens, for instance, if there is a polynomial which you have to destroy, so to speak, by a repeated integration by parts. But I'm sure you will see this at school. And that's it for integration by parts.